In this video, we'll start to look at heat engines, including their efficiencies. You'll notice that this slide includes take what you just learned about total heat and work. Well, that means we have to back up a slide. Let's look at going in a complete cycle on a PV plot. Now we had a graph where we started here and went and ended up in a different place, right? This time, we want to pick a starting spot. It doesn't really matter where it's at. This one's closest to me. So if I start here and go all the way around, ending up in the same place where I started, that means my initial pressure is the same as my final pressure, and my initial volume is the same as my final volume. And we showed before that if the number of molecules is constant, then we can rearrange PV equals NKBT to come up with PV over T is constant. So P initial, V initial over T initial has to be equal to P final, V final over T final. But we know P initial and P final are the same, V initial and V final are the same. That means T initial has to be equal to T final. So the initial temperature equals the final temperature. And if you remember, the internal energy of the system is related only to the number of molecules and to the temperature. If the number of molecules stayed the same and the temperature stayed the same, that means the internal energy has to be the same. So if the initial internal energy equals the final internal energy, that means change in internal energy has to be 0. And change in internal energy is Q minus W. So the heat put into the gas minus the work done by it. So if 0 equals Q minus W, that means if you go in a complete closed circle on a PV plot, don't let any molecules in or out, so a closed system, then the heat that goes into that system has to be equal to the work done by the system. Now we can go back to the other slide. Take what you just learned about total heat and work going through a complete cycle. So total heat is equal to the work done. Now, heat engine. The heat engine here is represented just by a gray circle. It's something that uses heat to do work. So to make a heat engine work, you have a hot side and a cold side. So if we think about a steam engine, a locomotive, the way it works is it's got a boiler. So you heat up water in the boiler. You're putting in heat, you get the temperature increase. So we have an outside of the steam engine temperature, which is the air outside, and we have an inside temperature that's higher. So in the example of a steam engine, it's taking heat in from the boiler, doing work to make the train go, and dumping heat out into the atmosphere. All right. So can we make an equation for a heat engine with Q hot, Q cold, and W? If I know the total Q has to be W, the work, let's see, the total heat going in, there's QH going in, so we're adding QH, we're subtracting QC. That has to be equal to the work done. So this is a mathematical model that goes with a heat engine. Now I'm going to draw the heat engine slightly differently. I'm going to take this gray circle and open it up so we can look inside. So this is the new gray circle now. So you can see what's happening is the heat comes in from here. Some of that heat is getting converted into work. And some of that heat goes out into the atmosphere. Now if you look at it this way, you can see that QH equals work plus QC. Or in other words, if we rearrange that, the work done is QH minus QC. Now if we look back, work is QH minus QC. Two different ways of finding the same thing. I think this is an easier way to think about it. So I will generally solve problems using this model not going back to internal energy. Now, efficiency. Efficiency means how much of what I put in went where I wanted it to go, right? What you want over what you put in. What is it that I want out of the engine in my train, right? What I want is for it to move, okay? The whole purpose of having the steam engine inside the train is to make the train go. So what I really want is the work. So the efficiency is what I want, that's the work, divided by what I put in. What went into here? QH. So this is now the mathematical model for a heat engine, where the goal of the heat engine is to produce work. You could then take this, work is QH minus QC, put QH minus QC over here, then you get QH minus QC over QH as being the efficiency. That's another way to write it, but I find it easier to just think about what do I want over what did I put in.